Okay, is there any sound? Right, so this is why I'm telling you that this is still the first try. So you know what happened is that there is a button that says go live on YouTube, and I forgot to click that. So we wasted 15 minutes. I am so sorry for that. So now that we have sound, let me reset this. Let me redo. So welcome to the first lecture. We will be discussing the admin matters for this. Yeah, I'm really sorry for that. This is my first time doing a scheduled live stream, and it's the setting is slightly different. Okay, so far I've been talking for 15 minutes, but apparently nothing goes through. Okay, so the prerequisites. So to really understand CS2102, you will need to know advanced programming. Okay, so the reason why we need advanced programming is because during the course of the semester, you will be doing projects, and most likely the project that you are going to do will be using JavaScript, right? So we will have a guide on how to do the project, and the guide uses JavaScript. Okay, so by hopefully having studied CS2030, you will be able to learn new language quickly. Okay, and the reason why we need discrete mathematics is because you need logics. Part of the module will be on functional dependencies, which is the analysis of your database. So most of this will be in a mathematical notation. So you will need to be comfortable in the language of mathematics. All right. So yeah, so hopefully you have taken CS1231 or MA1100, because these two have covered set, tuple, and relations. So relations will be the basis of our database, the relational model. All right, so that's why you will need the discrete mathematics as your background. Okay, and the learning objective, we have a few over here. On the design part, you need to be able to model a database. So given a problem, you should be able to model that particular problem using the ER model, or the entity relationship model. And hopefully you can analyze whatever problem we're giving you using functional dependencies. And afterwards, once you have come up with hopefully all the functional dependencies from your entity relationship model, you can try to improve on them using normalization. All right. So there's been a lot of requests to release the slide. The slide will be released after the lecture, because as you will see later, the slide actually contains a lot of typo. I do not want to release slides with lots of typos. Right, and yeah, so you will need to be able to create, modify, remove table using SQL query. Okay, and on the query part, you need to be able to retrieve required information. So if I'm giving you a certain information from the database that you will need to retrieve, you should be able to retrieve them using SQL. So that is our language of choice. Okay, and you need to be able to understand what the query is asking, and in particular using the tools we call the relational algebra. You will need to be able to check whether two queries are equivalent. Right? And on the project side, this is a big project. It covers 25% of your marks. I am reducing the difficulty by focusing more on the back end. So you need to be able to design your database correctly and well. The front end is minimal, but I do not want you to simply have HTML table. Okay, if you have HTML table, you will get most of the marks, but to get more marks, to get the full mark, you will need to go beyond table and do some little nice things on the design. Right. We also focus on collaboration, so I will want you to use Git. I will upload CS2103 slides on how to use Git. As for deployment, our main choice will be Heroku because it's free and it's freely available. So yeah, so it works well with Git, and it uses the tools that we ask you to install, which is PostgreSQL and Git, okay, and Node.js as well. There has been a few questions on the chat. No, so NoSQL is not going to be okay. Firebase is probably not okay. GraphQL is not okay. It must be SQL. All right. Notepad is definitely okay, but as long as you can connect to the Git. All right. So that's the learning objectives. The workload. So for a 4MC module, typically is around 10 hours. So unless I counted wrongly, the sum of this will be 10 hours. Okay, so lecture is 2 hours, which is what we are doing now. Tutorial will be 1 hour on Zoom. Assignment is not exactly 2 hours per week, but because we only have 3 assignments, which I will explain later. But roughly, during the semester, it will be about 2 hours per week on average. Projects also. I try to split the deliverables into 4 so that roughly every week you will have to do about 3 hours of works. Preparation is about 2 hours. Okay, so I will release a book. The book will contain the theory required in this module. I have written the book in 4 days. It is very concise. It is less than 100 pages. But it is only on the theory part. So that's why you will need to be kind of comfortable with the CS1231, because otherwise you may get lost in the notations. The lecture will be doing something that is mainly application or further explanation from the book. Right, so for this 5% of the weightage, I split into tutorial attendance. So please go for tutorial. Participation will be on the forum participation on Cosmology. So I will not open the forum on Luminous. So please go to Cosmology for your forum. Assignments, we have 3. So each of these will be 5%. Project, as I've said before, is 25%. Midterm is 15%. Final is 40. Okay, so final is pretty big. So yeah. Right, so let me clarify a little bit here on the lecture. The lecture, because we are using YouTube live streaming, it is actually automatically recorded, and it will be made available afterwards. So I will also post it on Cosmology. All right, so don't worry if you miss this. Everything will be recorded. Okay, and question will be via YouTube. Okay, so this is probably not comment. This will be via the live chat. So try not to flood the live chat. Right? Interactivity will be using Cosmology training. So if you have already signed up for the Cosmology, I will illustrate later what you can do in the cosmology. I think some of you have already tried to do it. Possibly we will have poll. Although I have not got this down yet, I do not know what app to use for the poll, so I will try to figure the poll later. But just note that there is about 5 to 15 second delay between the moment I'm saying things and the video being streamed on YouTube. So to make it less awkward, whenever I want you to do something on cosmology or doing a poll, I will try to talk more about the subject that we are talking about. All right, so you can try to do it while trying to listen. So hopefully you can do some kind of multitasking on that. But if you cannot finish the cosmology training, it's fine. You can do it afterwards. It will not be closed. And if you also try to do it after the lecture, you want to watch the lecture again, you can still try to do the cosmology training. All right. So yeah, so that's how we are going to integrate the interactivity between this YouTube live streaming and cosmology. Okay, and the focus of the lecture will be on application. And I've said the theory will be made available in books. The books will be ebook. Okay, I'll just upload the entire book onto cosmology. Right. Tutorial will be on Zoom. Hopefully you will try to discuss things. Otherwise, your tutor will just answer the selected questions. Right. So due to the time constraint, we will not be able to answer everything, and hopefully you can discuss the rest on forum. I will also monitor the forum so that I can answer those if required. Okay, and the hope is that it will reinforce the concept from the lecture. As for the individual assignment, so some of you would have probably learned from last semester about that fiasco of CS2102. So now I'm highlighting this very, very strictly. There is no plagiarism policy. Strictly no plagiarism. Okay, so you cannot plagiarize at all. Please try to do it on your own. That's why this is called the individual assignment. All right. So how many assignments do we have? We have 3. Okay, so this assignment 3 is wrong. It's not entity relationship model. So let me erase that first. The first assignment is on entity relationship model. It will be week 2 release. The deadline is on week 4. It will be 5%. Okay, so each of the assignment will be 5%. Assignment 2 will be on SQL, so you will have to write some SQL. The deadline is week 7. Assignment 3 will be on functional dependencies and normal forms. Again, it's also 5%. Right, now, whenever I say this, the deadline is on week something, what I meant is that it is on the Saturday of that particular week, and it will be on 23:59. Okay, and this 23:59 is actually quite misleading, because as it happened, whichever system I use, either it's Luminous or Cosmology, it's immediately append a 00 at the end. Which means if you have already seen on your computer that you look at your computer clock, it's 23:59, that means you have already late, because it will have probably been 01. Okay, so this is the deadline, which is on the Saturday, 23:59. So please very, very careful with this. Okay, so now for the team projects, I try to split the team projects into 4 deliverables. Every team must have exactly 5 people. Okay, unless the enrollment is not divisible by 5. Okay, then I will allow some groups to have fewer people. But that's this will be the upper limit. You cannot have more than 5 people. This is upper limit. The team registration deadline will be the end of week 3, and this will be on the Saturday. The second deliverables will carry a 5% marks. So what I want you to do on this particular part is that, well, I want you to give specification which includes constraint. I will tell you what kind of constraints do we want. ER diagram, you should have 15 total entity plus relationship. Okay, the combined total should be 15. There should be 3 non-trivial constraints, and there should be justification for any serial tab. So again, I will explain this later as we go through the semester. And then the deadline will be on the week 6, end of week 6. The system that you are going to use will be Git. Okay, so I want each group to set up a Git private repo plus Heroku. The Heroku can be set up later. If you do not want to use Heroku, it's fine. So for the Heroku, if you are not familiar with the Node.js, then you can probably try to use other hosting. The theme need not be from the same tutorial slot. So for the theme registration, it can be from any tutorial slot, because currently you do not know what your tutorial slot is. Okay, so I want your website to be live. Again, this is also good for you because it can be part of your CV, that you have this as your project work for the world to see. The third deliverables will be on the final report, which carries 15%. It will be at the end of week 12 or 13. Okay, if you need more time, then we will go with the week 13. Right, and on the report, it should have your work distribution, so which person do what, the ER diagram, again, which you should have already done before, the relational schema, which is the SQL on how you create it, the functional dependency constraint and discussion on the normalization, if any. Also, the description of the non-trivial constraint, like I said at the top over here. And what I want you to do is also, I want you to write down how do you enforce this with a trigger. And again, you just have to rewrite the justification for the serial type. And then we're going to do the Q&A at the end, which is using a demo video. So try to demo how your website works, and we will do a Q&A via Git, the Git comments. If I have any questions for you, I will post it on Git, and then you can reply it by week 14. Hopefully, this is the exam week, so hopefully you are not too busy by then. But we cannot help doing this if the final report is on week 13, because it will take time to read the report. Okay, so there's a few questions on the live chat. Will we be querying from the front end directly into the DB? No. So there is the intermediate part, which is the back end that connects between the front end and the database. We will have a guide on how to set the back end using Node.js, and the hope is that you just have to learn one additional language. If you're comfortable with Python instead, then you can approach me. I know a few things about creating a server using Python. Minimal, but there is something. Hopefully, I can guide you to the right resources. Okay. Well, there's a follow-up question. You do not have to build an API. So the API, you can use any libraries that you want. Okay, and all the files will be on the server, which is why we typically want you to use Heroku for the hosting, so that we can check your website, we can test your website, and from there we can give a meaningful Q&A. Okay, so that's for the team projects. And again, I'm just copying the plagiarism policy. You can try to find it here. I'm not sure if the link still works. I think they have a few revamp of the website. And this is just to show that when you accept the offer from NUS, you already accept that you are not going to plagiarize. All right. And lastly, this is the penalty for the plagiarism policy. Oops. So any student caught plagiarizing, they will be required to retain the module as graded. You will not be allowed to SU. So again, it's a very, very serious offense. Now, what constitutes as a plagiarism is that even you giving your answers to your friend is considered a plagiarism. Okay, and we have certain cases where, you know, you study together and you go to the restroom, you leave your laptop unlocked, and your friend just take photo of it. That unfortunately also constitutes plagiarism. All right, so you are responsible for safeguarding your code, safeguarding your answer. So even if it's accidental, it, again, because from what we see is that these two answers are similar. So if that happens, even if it's accidental, this part you must be very, very careful. So try to safeguard your answer. Okay, the tools. So you can start downloading this. I will upload the slide after, so you can get this link. This is Postgre. So all our example in the lecture will be on Postgre. This is Git, and as you know, this is Zoom. I am still quite unsure about this. Some of you will probably know what this is. This is Exemplify. I'm still not sure whether to use it or not. I don't really like that particular software, but it's probably good to have it. The last one here, so some of you probably know, is VLC. So why do we need VLC? So this is a very good question. We have midterms and final exam, which will be online, right? So how do we safeguard your integrity? Well, we use Zoom. We use Zoom to do proctoring. So your camera will be pointing towards your monitor and your back. The VLC will be used to capture your screen. So you will do a screen recording of your own screen, and then you will upload it. So we will give you how to use VLC to record your screen and upload it. Okay, so it seems like there is some kind of poll going on in the live chat that you do not want to have Exemplify. Okay, sure. We can have no Exemplify if you want. I don't really like Exemplify as well. Again, I'm still on the fence on Exemplify, but I guess most of you do not want Exemplify. Yes, Ubuntu doesn't support Exemplify. So yeah, so the VLC is going to be used for screen recording. So you will record your screen and you will upload after the exam, so that we can check for any kind of you know, it's just to make sure that you do not do anything funny. All right, the standard setting for any kind of assignment will be, oh, not assignment, for any kind of exam like midterm or final, you can only use a single monitor. We will make sure that you're using a single monitor without a secondary monitor. If you're using a secondary monitor, then unfortunately we will have to disqualify you from the exam. All right, and no, it doesn't have to be VLC as long as you know how to record your screen. All right, and again, we use VLC simply because there is a setting in VLC that allows you to record at 12 frames per second. So the file size is small. Right, so because the file size is small, you can then upload it to Luminous. Using any other screen recording, if you have gigabytes of video, then we cannot upload it to luminous, so you will have to upload it to YouTube. Give us the link. All right. So yeah, VLC is our preferred tool. There is a reference book if you do not like my book that I will upload later. This is the standard one that we usually use for database book. Okay. Unfortunately, I think the author has not updated, so the latest one is still the 3rd edition, and there is not going to be any 4th edition. There is this name, Shamkant Nafase. He was supposed to actually visit us and give a lecture on database, but unfortunately, he couldn't come because of our current situation. So yeah, so I'm putting it here because he's supposed to come. All right, again, the reference book are not necessary. So if you want, you can just use the book that I gave, and hopefully the content of the lecture will be clear enough for you to understand the content of the module. Okay, so that's it for the let me keep it. That's it for the first lecture, lecture 0. We are going to continue with some kind of introduction. So this is just a brief introduction on our topic here, which is on relational database. In here, I will also try to present what you can do on cosmology later, and what kind of symbols you want to look at that indicates that it has a connection to cosmology. Right, so we first start with a very simple question of, we're trying to define what is a database. Okay, so some author actually loosely define database, and some strictly define what the database is. Because there's wide variations of what a database is. We will not be defining it completely in this module, but we will arrive at a particular model which we call the relational model. Now, in the loose definition, even a file system like this can be considered a database. So if you see, there is a kind of a tree structure. This is the root of the database. Right, and then you have a pizza. Your database contains a database of pizza that has a name, like Diavola, Fungi, Hawaiian, Margarita, and so on. Okay, it is considered a database in a loose definition of database, and you can even have files inside to note what is the ingredient of this particular pizza. And if you open it, it contains data, right? So you have cheese, chili, salami that makes up Diavola. Right, but this is not how we want to represent a database. Okay, not a file system, not even a tree structure. There is another way to represent a database, and that is called a table. So a table is a kind of a natural representation of a database, and you will, if you read the book, you will see that this is basically just relations. So it relates a particular pizza with a particular restaurant. You can represent any relations using a table. Although the converse is not true, some tables are not relations, but all relations can be represented as a table. So that's why we use a tabular representation. And it is actually quite powerful. Okay, so let's take a look at another kind of what people consider a database, and this is more of a modern database. This is a graph. Okay, so graph is actually used in modern database as the underlying data structure. But for this particular graph, we can actually model it as a table. And this is what the table look like. So you have a user. So in this case, we want to look at a possible social network graph from the point of view of a user A. That's why he's highlighted in orange. So A is friend with B. So then there is an entry, user A is friend with B. Okay? Yeah, this is also known as a knowledge graph. If you represent that particular instance as a knowledge. Oh, there's a question of what's a graph. Well, if you have learned about 2040, CS2040 or CS1020 a long time ago, a graph is basically just a set of vertices and a set of edges. The edge connect two vertices. Okay, so that's basically what a graph is mathematically. Okay, and a graph can be represented as a table. And this table corresponds exactly to the edge. You can also extract the vertices. Assuming that every user is there on the table, then if you extract this particular column, then you have all the vertices. Alright, so that is a database, and what we have shown here is that a table is a powerful tool to represent most of the database, at least. Might be clunky. Alright, so no to stars. Yes, there is certain kind of thing that is hard. Okay, so the next question is, what is a data? What do we want to store in our database? Obviously, we want to store data, but what is a data? Now, this is a famous painting by René Magritte. It's called The Treachery of Images. The text at the bottom over here says that this is not a pipe. Right? And again, this may strike you as weird because, well, it looks like a pipe, but it says this is not a pipe. And in fact, Magritte is actually perfectly right in a sense that this is not a pipe. This is a drawing of a pipe. It represents a pipe. Okay, and this distinction is actually exactly what we are doing in computer science. In computer science, we are basically representing real-world objects as something that we can put inside the computer. You do not have a pipe inside the computer. This image resides in the computer, but the pipe itself is not. So what we want to do is we want to represent real-world objects, and we want to manipulate that representation. And to give you an exercise, so let's take a look at how we can represent this particular horse. Okay, it's a very beautiful horse, I know, but how do we represent this horse inside our computer? What can we do? Well, this horse is an image, so one way that we can represent the horse inside our database is to just put the image inside our database. But what kind of manipulation can we do with an image? So if you look at the image itself, if you try to open the horse, this is the horse file. These are actually binaries. How will you manipulate this horse? How will you say that this will be a different horse? Manipulation will be different if this is our representation. Okay? So let's try figuring out what kind of other representation can we do on this particular horse. Well, there is this one, which is quite nice, which is an ASCII art of a horse. It still looks like a horse, so you can kind of see from the image that this is a horse. It's a representation of a horse. You can put it inside the database, but again, manipulation will be very, very difficult. How do we say change the color of this horse? Currently, we do not store the color of the horse. So there must be some other way to represent data that still allow us to do meaningful manipulation. And the idea from Edgar Cott is that a data can simply be represented by the properties that we are interested in. So we take a look at this particular horse again. What kind of things we are interested in? Well, let's say we are interested in the color. The color is brown. Okay, what is the name of the horse? The name of the horse is, let's say, Star. What is the eye color of the horse? Black. What is the weight of the horse. Okay, so you can attach particular values into properties that you are interested on this particular horse, and you call that your data. It is a low resolution representation of that particular data because you lose a lot of other things. If you are not interested in the color of the mane or the tail, then you lose that information. Okay, so this is one example of the data representing this particular horse on 5 values that we are interested in. The color is brown, the eye color is black, the weight is 700 kg. Okay, so this I think should be roughly a correct weight for a horse. The name is Star. Okay, so it's a horse. Because like I said, it is a low resolution representation of this particular horse, then it doesn't really matter what kind of image I use. I can use this image. It should still be representing exactly the same horse. Because all the 5 values that we have are the same. In fact, I don't even need to have a picture at all. What I need to have is just a tuple containing those 5 values. This is my horse. And if I actually give you this particular information, it will become a representation of a horse. Now there is a comment on the live chat saying that you need a unique ID. Yes and no. You can allow duplicates, or you can say that, well, if there's any two that is the same, any two row that contains exactly the same values on all particular attributes, then it should be exactly the same horse, right? Because what we are doing is we are just representing a real world object. Our representation may not allow uniqueness. But what we are assuming in this particular module is that all real world objects that we are dealing with should be representable one way or another with the properties that we are interested in. In the case of your project, you need to be the one that finds such representation when you design your database. Right, so now, if I'm giving you another row, you know that this is going to be a different horse because, one, the color is different, the name is different. Okay, so I have a red horse over here because some of the properties are not the same. Well, in fact, only the eye color is the same. We know that these two are different horse. So this is our representation of a data. A data is basically becomes just a row in the table. And now your database will be the collection of those tables. So if I have a table like this is a more like a stable rather than a table. It contains lots of horses. Okay, I can have the same name, Star, the same color, but as long as one of this is different, I can assume that these two are different stars. They are not the same. Okay, that's what we want, right? So we want that every row, if they match on all attributes, they will be exactly the same real world object. Okay, there's a question, does the data have to be atomic? In this particular instance, yes. In a relational database, all the data have to be atomic. Okay, so how do you say that this is atomic? It's not atomic. You can break it down into 5 different letters: B, R, O, W, N. But no, that is not what we are interested in. What we are saying is that there is a value. I don't care how the value is being represented. There is a value corresponding to brown, which in a real world object, it corresponds to the color brown. Okay, in the sense, this particular brown cannot be decomposed further, because if I'm missing any one of the element, let's say I have a brow, it's not a color, right? So this particular data, brown, is atomic in that particular sense. Okay, so that is our representation of data, and that is our database. It becomes just a table. But there are other things that we are also interested in. Not all tables are useful to us. For instance, look at this table at the bottom. How useful is this particular table to us? It contains, every row contains 5 random integer, and every integer that it contains is 5 digits. But it's random. There really is probably not much of a structure over here, and in particular, we may not be able to assign meaning to this particular row. What is this particular row talking about in a real-world representation? Okay. So what we want is that for every row that you have a meaningful real-world object that you can map to. But again, this is more of a philosophical question, so we will not be fully answering this, whether this is an actual table or not. You can say that, well, this is a good table because it's a table of random number, maybe unit random number. A more interesting thing is this: we can kind of say that, well, this is definitely not really interesting, because even for this particular row, particular column, the type can be different. I can have a random string, or I can have a random number. The structure is kind of lost in this particular sense. All right, but again, it is more of a philosophical question, because if you really want this to be a proper table, you can actually say that, well, this is not a number. The first value over here is not a number. This is a string containing digits, and it probably has a meaning. If you have a particular mapping, then you can assign meaning to it. But most of the time, what you will have is a table of this particular nature, where it is easy to see how a real-world object corresponding to this will look like at a low resolution representation. Okay, so let's move on to the interactive part. Why do we need a DBMS? Now, if you see at any point in time, you see this on the lecture notes, it means that there is a corresponding training or exercises on cosmology. So let's try to look at cosmology. What we want to do is we want to look at the traditional data processing. Okay, you don't really have to do this. There's really no mark for you to do this. I'm just using this particular instance of Python to illustrate that the usefulness of using an SQL by comparing SQL with a traditional data processing. In a traditional data processing, you need to be able to control everything. You need to be the one that basically do everything. Okay, so if you don't really understand Python, it's fine if you do not want to do this, but let me just show you that if I have this particular specification, given that I have this particular table, you can look at crypto.csv if you want to look at how the data is represented as a table. What I want to find out is what is the monthly average for the given currency given as a string for that particular year given as an integer. And I already give you a lot of useful processing functions. Okay, so like map, filter. So this is just to simplify your work. But in an actual traditional data processing way, what you are doing is that you have to write all of this yourself. You as a user of your own traditional data processing software. But in the case of SQL, this is actually becomes a very simple SQL query. So you select this particular month plus the average of that particular component or attributes from the table that we say crypto. So this corresponds to the crypto.csv, where the currency is ETH. Okay, so I don't expect you to understand fully this SQL statement, but I'm just going to show you that if you understand SQL, then it is actually becomes much more simpler if you want to retrieve data from database. Okay. In comparison, if you have to do it on your own, this is what I did. Okay, I have an aggregate function that I look at every particular element one by one, and I check that they are equal to the first element. Right, that is my helper function. My helper function depends on the first element that is actually given. I'm passing another function, and I have a function to compute, and in this case I'm using it because I have a pivot. Right. In a traditional data processing, what you need to do is you need to open the database, extract the header, and extract the data. Okay, so the header is typically on the first row, and then you need to do some kind of manipulation to it. This one, again, it looks kind of simple because I already have the filter function defined, but if you do not have a filter function, then you have to kind of do a loop yourself and satisfying this particular property. So yeah, and at the end of it, you need to return it as a dictionary. Right? Yeah, so both are complicated, but hopefully once you finish the module of CS2102, you will see that, well, SQL is probably simpler. All right? So that's what I wish to show from this particular example. Now, there's another example here, which unfortunately is actually kind of harder to do from the SQL point of view because of the parametricity of the component. The component now is given as a as an input, but if we fix it to one particular component, then it is actually straightforward. So the reason why this one is actually harder to implement in SQL is because typically we do not have the attribute here or the component here as a variable. Okay, this is the one that is changed. We do not typically have those as a component, as a parameter. And there is a comment by Prof. Ui that there is a bug in Q2. Possible. I have this part which apparently is wrong. I should not have this. The index should not be from the open. It should be component over here. And I guess my answer key also uses this particular code. So again, it also shows that it is quite easy to make mistake if you write this codes rather than this particular SQL query. Okay, so that is the second part. The third part, again, if you want to update, now we want to make an adjustment. So instead of just reading from the database, we also want to write into the database. Now I need to give you an additional function called write database, and you need to give it in this particular format. If you don't give it in this particular format, this function will not work correctly. Okay? And the answer is also kind of difficult in a sense, but once you create a helper function, it probably simplifies things a little bit because I can use the map function. But notice that there's a map function that uses another map function. So again, the complexity is roughly higher in a traditional data processing because you need to give what is the computation that you want. In case of SQL, what you need to specify is actually not how the computation is being performed, but what is the final result of the data that you want. Okay, so what I'm specifying here is not how the database is going to compute this. What I'm specifying is that at the end of any computation that the database is doing, eventually I will get something where all these values are modified, multiplied by 1.2. So there's a question, are we going to build a DBMS from scratch? No, we are not going to build DBMS from scratch. This particular example is just to show you that building a DBMS from scratch is a tedious process, right? And there's another question, how is SQL coded? Well, it's a subject for future lecture. And if you really want to know how DBMS is built, you can actually take the continuation of the 2102, I think CS2223. They will teach you how to create a DBMS, in a sense. It gives you the inner working of a DBMS. So what I want to show here is that DBMS simplifies a lot of things. And that simplification is captured over here. If we look at how we are modifying that particular database, so in this case it's a CSV file, the kernel need to have a proper file system. The Python gave us a library called CSV. This is from the import CSV. I gave you a helper, but if I don't give you this two, you will need to write it on your own, how to open the particular database and how to write this database. Okay, so you need to then write the following 3 functions for those 3 particular problems. So the amount of work that you need to do from the user of a database point of view is that you need to write all of this. Okay, especially if I did not give you the helper functions. If you are using a DBMS, on the other hand, that bottom 2 of your responsibility is part of the DBMS. In fact, the DBMS is doing a lot more things. So here, instead of writing a function, you just write a query. You do not even have to specify how those data are going to be obtained. And this gives us a nice abstraction where, given a query, the DBMS can optimize. As long as you get your final result correctly, then it doesn't matter how those data are obtained, then that query is working. Okay, so the DBMS can optimize your query. But if you're using a traditional data processing, that optimization is not there. You need to write a function that is already optimized for that. Alright, so let's take a quick break of about 5 minutes. So we'll be back at around 1:12. And the reason why I need the break is because, you know, I need to go to the restroom. I've been drinking lots of coffee to ease my nervousness. Okay, so I'm really sorry for this. We have a 5-minute break. Okay, so we still actually have 2 more minutes, but let me try to answer some of the questions on the live chat. So why not use ORM to abstract even further? Well, we can, and that is exactly what kind of SQL is, right? But instead of writing it as an SQL query, you write it as an object. If you can have a mapping between this object and the SQL query, then they are kind of almost isomorphic, I believe. For Python, can just manipulate data with pandas library. Yes, you are correct. But all those libraries are someone has to write them, in a sense. And if there is no such library available for you, then your responsibility is bigger. But in the case of SQL, we know that given this particular representation, if you represent a data as a table, then you know the SQL can always be used. So why SQL over no SQL? Because SQL here has a very firm basis in logic. So let me go back to lecture 0 a little bit, since we are still at a kind of a, oh, actually not lecture 0. Let me go back to the top over here. Okay, so let me clear. Okay, so let's just use this. This is where the connection with the relational theory, the set theory, is present. So if you look at any one of these attributes, it becomes a set, S1. This one becomes a set of S2, and so on, right? So why is table also called a relation? It's because to get this two particular value, star and brown, and again we ignore the rest first. What you are doing is you're basically doing a Cartesian product on these two, S1 and S2. Okay, and a relation is simply just a subset of this. Why is it a subset? Because the full Cartesian product will give you a lot of things, but not all of them are useful. And this firm grounding on logic gives us certain advantage on when we analyze table, and that's where your discrete mathematics will come in useful. Okay, so there's another question: which version of PostgreSQL to download? The one that I'm currently using is 11.4 or 11.5, but it doesn't really matter which one you're using. I would probably suggest using the version 12. Then I'll update mine to version 12 as well, so that we will be on the same page. 12 is the latest, so maybe we should just use that. Okay, so let's continue on this. Okay, so in fact, what I've shown you before on how to create that particular relation can be used over here as well. So here we're going to analyze data. We're going to create a database from that particular set. So what we can do here is that we split each of the component, each of the attribute, each of the property that we are interested in, into 5 separate set. Okay. You can give a name which is the same as your attribute name. So this is a set called name, this is a set called color, the third one is a set called weight, and so on. And what you will have to create, in the end, what you will get to create this table is that you create a relation such that you do a Cartesian product of all of this. And this particular table is a subset of those. So let me give you an example. The third one, the third row, is formed by taking this chain from the name, the color white, the weight of 758 kg, the length of 188 cm, and the eye color of brown. Okay, so that is how you create this particular row. Each of these is a set, so this one is an element of the relation. Right, so again, we say that we x, Cartesian product, Cartesian product, Cartesian product. This relation is a subset. So what is this particular row then? This particular row is just what you call as a tuple. What is a tuple? A tuple is kind of like a set, except that your position matter. It must be in this exact position. Okay. So in a sense, what it means is that a tuple, usually using an angled bracket like this is different from 2, 1, because the position matters in a tuple. Okay, so that is how we create the data. Now, if we are looking at a table from this point of view, we can give a name to elements of the table. Once we have a name, our discussion hopefully will be simpler. So we call this an attribute. We call it a component before, we call it an attribute. Every element in the table, except for the header, is a value. Okay. This value belongs to the set of this particular attribute. So the attribute is mapped into a set, or the name of the set. The value belongs to the set. It is an element of the set. If you have a sequence of attributes, you can actually describe a table. So that is what we call a schema. A schema is simply a sequence, an ordered sequence of attributes, and that is really what you need to know about the table. Well, additionally, you will probably need to know the type. Right? And if you extract a single column without the header, this is what you call as the domain. Every value in the domain must be an atomic value. Okay? And we represent this as a set such that we remove duplicate values. We have 188 and 188. We remove one of them because we don't care about duplicates. That's what a set is. So this one is a tuple, also called the particular data that we are interested in, or we can also call it a row. So every row becomes a data. A collection of those data becomes a database in multiple tables, of course. There's also a few things that we are interested in, like if you look at the schema, how many attributes does it have? Well, the number of attributes is what we call as a degree or the arity. This really comes from the set theory, where you have a relation. If you do a Cartesian product between S1 and S2 only, it has an arity of 2 because you're using 2 sets. Okay, and S1 and S2 can be the same set. So you can have S Cartesian product with S. If you have one more, this will have an arity of 3. Right, so the number of attributes is your arity. The number of rows is your cardinality. Okay, so we don't really use cardinality, but the arity is quite important, because in our case, the cardinality, we assume it to be can be infinite if you have enough hard disk on your computer. And so what do we mean by a relation instance? Every single table is a relation instance. The schema is the header. So it describes the structure of your table. The instance itself is the collection of this data together with the header. It is one particular instance. There is something that we want from this particular instance, or any kind of instance, is that the instance must be valid. What do we mean by valid? Well, all the data must satisfy constraints. Okay, what kind of constraints? Well, you do not want to include a horse that somehow have a negative length. That is an invalid data. So if you want to have a valid relation instance, all the data must be valid. There are two things about validity that we will explore later. One is, how do you enforce validity? So given that I can specify a kind of constraint, how will the database actually enforce this constraint? And the second one is, how do you find the constraint? How do you, if I'm giving you a valid instance, how do you actually try to figure out what are the constraints? So there is a kind of inference. It is actually more of the work of data mining rather than a database. But we will do that kind of reasoning later. A minimal version of those kind of reasoning. Now, if you have multiple relation instance, let's say this is 2, this is what we call a relational database. Right. Again, the name here and the ID is random. And what we mean by a relational database schema is that, well, you ignore the instance itself. So relational database is talking about the instance. A relational database schema, you ignore the instance and you just look at the header. The relational database schema is really what you need to know about a particular database, such that you can insert something into this particular database that satisfies the structure. Okay, so that's a database. Additionally, besides just looking at the schema, because the schema enforces a kind of a constraint, what we call a structural constraint, if you want to insert something into the relational database satisfying a certain schema, you have to follow that particular structure. If you want to insert into this table, you have to have a name, color, weight, length, eye color. Sometimes you also want to enforce additional constraints, such as the domain or the data types. Okay, so again, as I was about to say this, there is a question on it. Are data types part of the schema? It is actually part of the schema, but most of the time we assume that the data types are known, so we can safely omit them from the schema. If you look at this, the name, we can say that, well, the type of this is kind of a string. Okay, in the language of Postgre, I think this is called a varchar. And there should be a string type also, but typically what we use is a varchar, variable character. The weight, if we ignore the kg, and the length, if we ignore the cm, they can be represented as a integer. Okay, so those are the kind of constraints that we want. So the second one here, the second table over here, also satisfies a kind of a what we call a domain constraint, the type constraint. But if you look at the last one over here, the type might not be so meaningful, because if you want to represent this as an integer, the second one is wrong. Okay, so this gives a kind of a credence, that a kind of a confidence to us that this is not a proper table. But of course, you can always upgrade this into a varchar. Then everything will be a varchar. So what I want to show in this particular third example is that not all tables are meaningful. And again, what we want is we want to look at only meaningful tables. Now there is a question that is asking whether relational DBS are really just that they are the same number of arity. No, it's not. Okay, so here the two examples that I use have the same number of arity, which is 5. But it need not be the case. I'm just using 5 because I make a nice box. But I don't need to have phone over here. Let's say I don't have a phone, then the arity of the bottom one is 4, the arity of the top one is 5, they are still a relational database. Right? Oh, it seems like the third table is cut off from the live stream. So yeah, I'm not sure how to expand that, but at least I know not to use this particular part of the slide for future use. But this is exactly the same table that I used before, where I have different kind of data types in different rows. Okay, so hopefully you can remember the previous table that I show. Right, now there are other kind of constraint, a few that we will discuss. The first one is what we call a superkey. The idea of a superkey can be generalized into functional dependencies, so we will not go into this in more details, but this is kind of like what is the idea behind functional dependencies, FD. So what I want to know is that if I am giving you an empty row such that I only have a single value filled in, can I fill in the rest? For this particular question, the answer is yes. For the color red, the only value I can have over here is Dakota. The only value I can have over here is 813. Here is 188, and the eye color is black. And also remember what we said before, that if two rows have exactly the same values on all attributes, they must represent the same real-world object. If I can do that with just a single value on an attribute using any possible values within this particular attribute, then I call that particular attribute as a superkey. It means that it can identify the rest uniquely. Okay? So if I'm giving you the color red, I can only have a single value for this particular row. So does that mean color is a superkey? So we shorten this as SK. So that is the question. Unfortunately, it's not, because there are a counterexample where I have a brown. If I'm asking what is this brown horse, I have two possible answers. One is that I have a star and I have a Misty, which should have been a star, but it was accidentally changed. Different weights as well, different length, and different eye color. So there is not a single answer to this particular question, where if I leave everything else blank, I only give you the value of a color, I cannot uniquely identify the rest of the attributes. This can be either star or Misty, 758 or 813, 90 or 93, either black or brown. Okay, it's not unique. Which means what we know so far is that color cannot uniquely identify the rest. But what if we expand this? Instead of just giving you the color of the horse, I'm also giving you the eye color of the horse. Now this is unique. At least for this particular instance, relational instance, if I only know the value of these two, it can uniquely identify the rest. I know a single row. In this case, it's Misty, 813, and 193. It is no longer star. Right, so before we move on to what the concept of superkey is, there is a question here. For relational database, does there need to be a relation between the different tables? No. There need not be relation between the different table, because I can have multiple projects going on in a single database. Although that is not really what we want to do in this particular project, but sometimes you may want to have a table that is slightly separate from the rest, if you want, and that can be used as a kind of a what do you call that? Like logging. Logging need not be related to the rest. Okay, now let's move on to the concept of the superkey here. So adding more known attributes will definitely narrow it down further and further into a single row. So eventually you will actually have at least a set of attributes that will uniquely identify any single row, and that is the entire schema. Because based on our earlier definition is that if we have two rows where all the values are the same, they must be representing the same real-world object. Okay, so a superkey is basically an identity. But an identity, at the worst case, like I said before, can consist of everything, which is not exactly useful. Having all the attributes as a superkey is not useful. So is there any other notions that we can use? Well, yes, and this is where the notion of a key comes in. So let's take a look at the different examples over here. Let me show you a kind of possible queries that we can ask on this particular table. So on the first one, I want to know if I'm not giving you the ID and the phone, can I still uniquely identify these two values? For this particular instance, yes. Okay, which means that the name, the weight, and the height are superkey. So let me use that notation. Name, weight, height is a superkey. But let's say I try to be more adventurous. If I'm also omitting the height, which means now I'm representing the name and the weight only, is this a superkey? Unfortunately, no, because again, the weight here can be a duplicate, and the name can also be a duplicate. So this particular set is not enough to uniquely identify the rest. So this is not a superkey. But if I try the other way, if I'm missing out on the weight, so let's say only the name and the height, can this uniquely identify the rest? Yes, because for our particular instance over here, the height for the two anesthesia are different. Okay, the last name is definitely different, so I can always identify any two rows within this particular instance if I know the value of these two attributes. Now, what is the property of this particular superkey that is not in this particular superkey? And that is that this superkey at the bottom is a subset. So this is a subset of the one at the top. So a key must be minimal. And what do we mean by minimal? Minimal means that if we remove any single attributes, it will no longer be a superkey. So we look at this. The name and the height. Is this actually a key? The answer is yes, because if I remove n, I only left with h. The height will no longer uniquely identify the rows. So this one is not. If I look at the name, can the name uniquely identify any rows? The answer is no. Okay, so the removal of any one of these attributes will no longer give us a superkey. Yeah, so a key is a minimal. Minimal in the sense that removal of any single attribute will no longer make it a superkey. ID is a key because all the IDs are unique. So this is where the two types of questions are more apparent. One is the notion of enforcement, and the other one is the notion of inference. What we have done so far is to infer what are the possible keys. We know that this is not a key because this is not the minimal. But this is this actually, for this particular one, it is a possible key because a removal of any one of those means that we cannot identify a single row. But is name and height truly a key? So that we do not know. It really depends on how the database is first created. Okay. So there have been a few questions of this nature about primary key and super key. Primary key is not actually a super key. Primary key corresponds more towards a key. But there is a different kind of concepts that we want to explore further. Here is that the key need not be unique, as a super key need not be unique. We say that N and H is a key, while at the same time ID is a key. So we have two possible keys. This is what we call some minimal, not minimum. Okay, the difference between minimal and minimum is that for minimal, you try to remove it, it no longer satisfies. Minimum, it must be the smallest. Okay, so key and super key are not interchangeable. A key is a minimal super key in the sense that it is a super key such that if you remove any single attribute, it no longer becomes a super key. So that's why the name and the height is a super key, but also a key. The name, the weight, and the height is a super key, but it is not a key. ID is a key, and by definition it is minimal because we cannot remove ID. Okay, so we have two keys. What we call this is, they are called candidate keys. Why they are candidate keys? Because technically any one of them that we choose can be primary key, right? So the notion of primary key is basically a candidate key that we choose to be the key that we want to enforce the database. All right, so primary key is basically your own choice. If a problem that you are facing may have multiple keys, you can choose any one of them to be the primary key, right? And this is what I say, that the key is actually just a minimal super key. So I will add into this slide later to give the notion of what it means by being minimal. But minimal is basically if you try to remove any one of the attributes, you no longer satisfy the question. But it is not the minimum. Okay, minimum means that it must be strictly the smallest. Okay, and this is the concept between the global and the local. A minimal means that it's a local minimum. That's why it's a minimal. A minimum is a global minimum. There might not be a unique minimum, and definitely there may not be a unique minimal. Okay, so minimal super key. You remove any one of those. So if you look at this, this one is not even a super key. This one, it is a super key, but this is a smaller super key. Right? So again, a super key need not be minimal. That's why there exists at least one super key, which is the entire schema. For a key, it has to be minimal. Okay, there's no other choice. It has to be strictly minimal. If I try to remove any one of these, either the height or the name, it no longer a super key. So that's why this is a key. Right, so again, this is just to give you an introduction of what the kind of constraints we are looking at in a database. We will go into more details about this super key in a broader context of functional dependencies in a future chapter. Okay, so don't think too much about this. It is best to come up with a practice. So again, we have a practice. So let's look at what kind of practice are we looking at over here. This one is about the super key. So here, I want you to figure out what are possible super keys over here. Let me give you a brief way on how we can actually do this. It says possible. Right. In the realm of possibility, if I do not find any kind of violation, then it is possible. So what we want to look out for in this particular case is whether there is any violation. Okay, what kind of violation are we looking at? Well, you look at the course ID. Let's say we want to know whether the course ID is a super key or not. Well, we look at this. These two values are the same. Can we use it to uniquely identify the other two? Well, no, because these two have different values. So clearly, the course ID cannot be a super key. Okay, and similarly, student ID is not a super key because again, for the same value of student ID, we have different course ID. So what we're looking for is violation. And this brings us to something that is very, very nice, which is the grade. The grade are all unique. This uniqueness means that there can be no violation. So grade is definitely part of the super key. And once we know that a grade is a super key, any superset that contains a grade will definitely be a super key. Okay? The other thing that we can look for is that, well, the combination of a student ID and a course ID is unique. So it also becomes a super key. Alright, but again, this is only possible because we are looking at this restricted instance. If you add more, we have more inference that we can do. The set of possible super keys narrows down. Okay, so if you submit this, you get correct. Okay, and it may not be logical. Why will we say that the grade is a super key? In most cases, it cannot uniquely identify. If you add more, definitely there are going to be people with the same grade. But we are talking about the realm of possibility here. We are not talking about the realm of common sense. And we are looking only at this particular instance. And if you continue, the second one is about the key. Now, we know that grade is a super key. And based on a previous discussion, well, anything containing a grade is a super key, which means they cannot be a key because they contain grade, and grade is minimal. So these are no longer keys. And the only key that we can have, the only other key that we can have, is a student ID combined with the course ID. Okay? And these are the only two possible keys, because any other combinations that you are looking at will contain as a subset either a pair of student ID and course ID or the grade. Okay, so this is the second part of the problem, which is about enforcement. So I'm leaving it as an exercise for you. So try to do it. If you get something wrong, I think there are some hints that I am giving, but I'm not sure whether it will show when you click submit or not. So yeah, so that's the super key. Now, the next notion that we are looking for is what we call a foreign key. A foreign key is also called as an existential dependency. A value on a particular row depends on the existence of another value, either on a different row of the same table or a different row on a different table. So let's try to minimize this. Currently, there's no connection between these two. These two tables are not related at all. Let's try to form a relation between these two tables. Let us simplify a horse into just the name, color, and eye color. This is a person, what we call an owner of the horse. This is another table that relates between a particular person and a particular horse. We want to give a meaning of this particular table is that the person with this particular ID, which is this person, owns the horse called Cheyenne with a white color and a brown eye color. That is what we meant by every row in this particular table. Now you notice that there is a stripe over here, and that means that we do not know about this particular horse. This horse may or may not be owned by someone. The first horse, star brown black, is not actually owned by anyone. It's not even on the table. Okay, so there's three things that is happening here. One, we know for sure a particular horse is owned by someone. We have that value of the ID. Second, we do not know whether any person owned the horse. The third one, we know that the horse is not owned by anyone because it's not even in this table. This is what we call as a null value. We will have a kind of practice on a null value later. First, a little bit of terminology. A table that is being referenced is called a reference table. A table that is referencing on something is called a referencing table. We have two reference tables, and we have one referencing table. You will kind of see later in the tutorial that the reference and the referencing table may not be different table. A table may refer to itself if you want it, and there's a use for that. Okay, so we will try to explore that in the tutorial instead. So okay, so for a foreign key to be enforced, we have two conditions. One, either it exists, or second, we do not know. It's a null. So that's why this is okay. It can reference this. It's fine because we do not know whether it exists or not. And unfortunately, this particular part on the null may make things a little bit confusing, which we will illustrate with the training on the foreign key. So here's the one that I'm giving you as an exercise. The one that I want to focus more is on the second one. Consider this particular relation that is being referenced, and I am referencing it using this particular schema. Okay, the student ID is referencing this course ID is referencing CID. Which of this can be inserted without violating the foreign key constraint? The main thing here is if any one of this value is null, I have two values that are currently referencing at the same time, these three are immediately valid. Okay? The reason is because you do not know whether it might exist eventually or not. So you have to keep this, even though one of the value is null. And even though 313 does not actually exist. Okay, so as long as one of the value is null, you have to accept them. Okay, so if you're stuck on this particular training, then I'm just telling you that this 3 should definitely be part of the answer. Okay, so that's one behavior that might be counterintuitive. Okay, so what is null? Here we want to talk about the peculiar property of a null value. This is what we call a Boolean null. So null can actually exist anywhere as any type. There is an interesting question by Prof. Ui. Can a column be a primary key if there's one and only one row with null? Actually, this is what I found interesting, is that the older specification of SQL actually allows null to be part of a primary key. And the newer standard of SQL disallow null completely from being a primary key. Part of the reason why they disallow null is partly what I'm going to explain over here, is that null has a very weird behavior. And this is the behavior that we're going to explore on what is weird about null. But again, because null can be of any type, we first talk about the simplest kind of null, which is the Boolean null. So if there is a ball, I call this true. If there is no ball, I call it false. What a null value is that if I don't even know if there is a ball or not, by having a closed box. So I don't even know, it can be yes, it can be no. Okay, but at the logical level, there's actually something that is slightly different from here, is that null is not equal to either one. It's not equal to both, in fact. So it is different from true, and it is different from false. What kind of operations can we do on a null? Well, can I say that this is true? So this is just ID, identity. Can I say that this is true? Well, it's not, because I do not know whether this is empty or not. Can I say that this is not null or not empty? So if I try to negate a null, I want to know whether is this not empty or is this not filled. Okay, so if you try to negate a null, your answer is also null, because you do not know. You cannot open the box, so you do not know whether it's empty or filled. So if you try to negate a null, what you have is a null. There are other operations, which is the binary operations, which is, you know, AND and OR. The kind of questions that I can ask with an AND is that, is both boxes contains green ball? Well, it's definitely true over here. I'm not sure. This is definitely false. This is definitely false. This is definitely false. This is definitely false. And this is definitely false. And for everything else, I do not know. Okay, so if I say null and true, which corresponds to null and true, which is this, the answer is null, because I do not know. I do not know if both boxes contain a green ball. Now let me use a different color for OR. This corresponds to the question, is one of this contains a green ball? Well, it's definitely true over here. Definitely true over here. I don't care what this is. It's true here. It's true here. It's true here. This one I do not know. This one I do not know. This one I do not know. And this is definitely false. So that's an OR. Okay, and notice the symbol at the top. You can try it on your own. We try to move on to where things get more interesting, which is when we talk about numbers. In the concept of numbers, we can also insert null. If there's no ball, it's a number 0. If there's one ball, it's 1. 2 balls is 2. 3 balls is 3. So what is null? Again, null is a closed box. How many balls are here? I do not know. So that's the meaning. So then I can ask a few questions here. What is 1 plus 2? Well, the answer is must be 3. What is 2 plus? I don't know. This one must be, I do not know. So what is this? What is this value? This value corresponds to the closed box. Okay, so if you try to add a null into any number, what you get is a null, because you do not know how many values are there. Something more interesting is that if you try to compare using a less than or greater than, is 1 less than 2? Well, the answer must be true, so what we get is yes, or a green box, a box containing a green ball. Is 2 greater than whatever this is? The answer is we do not know, because if the box somehow contains 1, then it's not. If the box contains 3, well, if the box contains 1, then it's yes. If the box contains 3, then it's not. So this one we do not know. But what is this do not know? This is a closed box, but notice that we have a change in types. This is an integer. This is an integer. This is a boolean. A null can be of any type, so they are still represented by the same null, but the type can mean slightly different. Okay, so is 2 greater than null? The answer is null, but it's a boolean null. Right, so there's a slight change in meaning. And this is the very weird property that I'm going to go about, which is, are these two equal, or are these two not equal? So think about it for a moment. Are these two an equal value? So in the case of an integer, in the case of integer, does these two contain, so this question is basically, does these two contain exactly the same number of balls? The answer is I do not know. What this symbol means is that you can ask the question, does this two contain a different number of balls? The answer is still I do not know. So this is where it's weird, because when you compare two nulls and you check whether it's equal or not equal, you do not know whether they are the same or not the same. This is part of the reason why primary key was eventually in the specification of SQL, eventually they say that a primary key cannot be null because of this weird property. How do you say whether you want to enforce a null? When you allow primary key to be null, how do you know that they are different from another row, if that is the only primary key? Okay, so this is why null is weird, and this is why primary key eventually cannot be null. But the older version of SQL actually allows primary key to be null. But we are following the newer version where primary key cannot be null. Okay, so that's basically it. Except that we now have a last symbol. In the context of SQL, this is called isDistinct. Okay, so isDistinct is a very special construct that is present when we are dealing about null, and that is because what we want to do is we want to treat a null value as a value instead of an unknown value. So this is really the last one, is that when you say that null is distinct from null, the answer, well, this one is actually not distinct. It's not distinct. The answer is actually yes. Okay, so we want to have an operation such that we want to be able to produce a known null value, and this operation is what we call as a is not distinct, and this one is distinct. Okay, so sorry for dragging a little bit. So that's it for the lecture. So thank you for coming. I will try to look at the live chat, and then I'll try to incorporate all of those into the lecture so that you have a more complete lecture notes. So and then I'm going to post the corrected lecture notes together. So I will have two versions. One is without the annotations that I have, and the other one is with the annotations that I have. I will put it onto the cosmology. Okay, so that's it. Thank you all for coming.